last video for tonight with the really quick stuff we can do with our equilibrium constants. So this has to do with manipulating or changing given values of the equilibrium constant. So let's go back to that equation we were looking at before, where we have 1 mole of dinitrogen tetroxide in equilibrium with 2 moles of nitrogen dioxide. And if we were to write the expression for this, we would write it as Kc equals concentration of NO2 squared divided by concentration of N2O4. Now, let's say we just decided that we were going to multiply this equation by a coefficient of 2. So now we'd have 2 moles of dinitrogen tetroxide and 4 moles of nitrogen dioxide. If we were going to write the expression this time, we would take the concentration of NO2, raise it to the 4th power, divided by the concentration of N2O4 squared. So what would happen to our value, like if we used kind of easy numbers for this, is this answer would change by a power of 2. So that's our first rule for manipulating these values, is if you multiply an equation by a coefficient. So if you multiply an equation by a coefficient, and when I say coefficient, I just mean some number, and I'm going to call that coefficient n. What you will do is you are going to take your original equilibrium constant and you are going to raise it to the power of that new equilibrium constant to get your new equilibrium constant value. So let's say that this, when we solved, let's say that this were 2. So what we would do is we'd take our original, we multiplied it by, let me see if I can stick this in here. Our original was 2. We multiplied this equation by 2. So we'll raise that to the 2 power, and our new equilibrium constant would be 4. If this were, let's see, let's say it were 10. We would take our original, which was 10. We multiplied it by a coefficient of 2, so this will become 2. So this is going to be 10 squared, and our new value will be 100. So that's our first rule. Let's go on and let's do our second rule. So, well, let me go back because I'm going to talk about this one more time. Likewise, if you decided that you wanted to sorry, I'll fix these lines. Let's say that instead of this being 1 and 2, we wanted to divide it by 2. So this will be 1/2, and this will be 1. So what we're doing in this case is we're not multiplying it, we're dividing it. So what would happen here is instead of NO2 being raised to the 2nd power, it's going to be raised to the 1st, and this is going to be raised to the 1/2. So if we want to come up with a rule for that, we could say that rule number 2 would be if you divide an equation by a coefficient, And when I say a coefficient, I mean a number, and I'm going to do n. What you'll do is you are going to take the original equilibrium constant, and you are going to raise it to 1 over the nth power, and that will get you your new equilibrium constant. So let's say our original equilibrium constant was, I think we did 16 on the earlier slide, so let's say this was 16. And let's say we divided our equation by 2, like we did in that example. So I would raise this to the 1/2 power. And then when I solved that, I would get my new equilibrium constant, which this is the same thing as taking the square root. You guys would be able to do this on a calculator, so you would get 4. And I'm not good at doing math in my head, so I really hope that's right. You guys can correct me tomorrow if I am wrong. Okay, the next thing is, let's say that we have an equation. And let's go back to that same one that we did before. So N2O4 in equilibrium with 2 moles of NO2, and we want to reverse it. So we're going to write this in the opposite direction. So we're going to say 2 NO2 gas in equilibrium with N2O4 gas. Now, if you really think about this, what you're doing originally here, you've got Kc is going to have NO2 concentration squared divided by N2O4 concentration. That would be for this reaction. If I reversed it, I would have, let's do green, sorry. K sub C equals, now N2O4 is in the numerator, and concentration of NO2 squared is in the denominator. So if you look at what's happened here, you've basically done the inverse. You've flipped it over. So we want to make a rule for that. So rule number 3 would be, if you reverse an equation, what you will do is you are going to do the inverse of your original equilibrium constant to get your new equilibrium constant. So if I go back to the previous slide, this one, and let's say for the one that I wrote, the reaction or the equilibrium expression that I wrote in orange, let's say when we solved for this, we got, let's say we got 4. So what I would do here is I would do the inverse. So I would say 1 over 4 would give me 0.25 as my new equilibrium constant for the reaction in reverse, which should make sense, because if the reaction, let me erase some of this stuff. Let me get rid of this. And let's just talk about how for the reaction that I wrote in blue, if the equilibrium constant for this was 4, you know that it's shifted toward the right, so it's product favored. Well, if we want to talk about what's going on when that reaction is reversed, this direction is not as favored So when I look at the value that I get for this, it's telling me it is reactant favored, which tells me I have more NO2, which is the same thing that I was told up here by that number that we solved for. Okay, last rule, I think I'm just going to tell you this one, is if you are given a series of equations, so if you have two or more equations and equilibrium constants for those equations, the net reaction is the sum of the two equations and their equilibrium constants are multiplied. So if I have two reactions, I'm adding them together, and I have equilibrium constants for each of those. I'm going to take those two constants and I'm going to multiply them together. So let me do a quick example of this. Sorry, I'm going to change the background. All right, so let's say I have HF in aqueous solution. That's in equilibrium with H plus, which is in solution, and F minus, which is in solution. And I am given a Kc for this that is 6.8 times 10 to the negative fourth, which makes sense. Small equilibrium constant for a weak acid. And then I am also given another equation in here. Whoops, don't want that. I have oxalic acid, which is also another weak acid. So oxalic acid is in equilibrium with 2 protons and 1 oxalate ion. And the equilibrium constant for that reaction is 3.8 times 10 to the negative 6. And what I want to do is I want to determine the value of Kc for these two reactions added together, which if I were to do that, okay, the example I'm looking at in the book has taken this equation right here, and they have reversed it. So what that would tell me to do, so let me go ahead and write the reaction first. So I'm going to have 2 moles of HF. So that tells me that this reaction has been multiplied by 2. I have 1 mole of oxalate, which is confirming that this was reversed. That is in equilibrium with 2 moles of fluoride ions and oxalic, 1 mole of oxalic acid. Okay, so this first equation, let's do green, you can tell has been multiplied by a coefficient of 2. So what I need to do is I need to take this and square it. And then this equation was reversed, so I'm doing the inverse of this equation. Or that, I'm sorry, not that equation, that equilibrium constant. So what I will do is I need to make some room on here. So I need to find out the answer to this, what that value is, and I will need to find out what this value is, and I will need to take the two of those and I will need to add them together. So this one right here, 6.8 times 10 to the negative fourth squared is 4.6 times 10 to the negative 7th. I just misspoke. I said that I was going to take these two and add them together. I am not. I am going to take these two and I'm going to multiply them together when I get those values. So this answer here is this one. Okay, I'm going to switch colors. But have not, I'll use yellow. So I'm going to take my answer to this, and I get 2.6 times 10 to the 5th power. I'm going to multiply those two together. And when I do, I'm going to have two significant figures. And so my answer is going to be 0.12, which tells me it is reactant favored. So it tells me that I have more reactants, or the equilibrium is shifted to the right.